Hello everyone. Today's video um, is video number 2 on photolithography. Um, Yesterday I introduced the general process and focused on generating the image on the surface of the photoresist. Well, I guess before I'm just going to jump into things. Let's go ahead and I'm going to go ahead and share the notes. Okay. So yesterday we covered the first part of photolithography. Remember, this is the process of reproducing a pattern on the surface of the silicon wafer. And we talked about optical sources, arc discharge lamps, excimer lasers, to produce those the shortest photons possible, deeper and deeper into the UV. That light is shined through a mask that has opaque and transmissive regions and is incident on the wafer and photoresist. So yesterday we talked about the nature of light and how it diffracts when the openings that it is transmitting through are on the same order as the wavelength of light, and that diffraction creates these spherical wavelets and interference at the photoresist surface that distorts the pattern that we're trying to create. And this distortion gets worse as these spaces get smaller relative to the wavelength of light. And so as we're pushing the technology to make smaller and smaller features, either we have more distortion, right, which limits our ability to make those small features reliably, or we transition to a lower wavelength and keep that balance still in favor of reproducing the pattern faithfully. We introduced ideas of this modulation transfer function, which takes these sorts of patterns and places them in close proximity to one another. And so you never actually go to zero because you start to get light from the adjacent opening. And we'll revisit this because this maximum level and minimum level has implications for the sensitivity of the photoresist. There's a maximum and a minimum amount of light required for the photoresist reaction to occur. Let's see, jumping ahead, we talked about different ways of arranging your masks and surface. You can have them in contact with a gap, or projected, or light projected through the mask via optics similar to a microscope. And there are trade-offs for each of those, mainly the presence of defects versus the presence of distortion. Okay, so yesterday we were concerned with getting the light to the surface, right, and all of the factors that are contained within that. Now we're going to cover what happens at the surface. So that would be photoresist, and after this, so yeah, mostly photoresist. Then I'm going to jump in and talk a little bit about chapter 9. So that is advanced lithography, specifically other radiation sources, electron beams, and X-ray sources. So as I mentioned yesterday, in the diffraction limited case, right, when we're talking about the diffraction distortion, you're limited in size of feature by the wavelength, like I I said that over and over again. And so to get smaller features, eventually we're going to run out of tricks to continue to get incremental increases out of our UV systems. And so transitioning to a particle or photon with a much lower wavelength essentially kind of resets the clock if you can figure out how to build a system based on that wavelength. And two good options are electrons, high energy electrons, which have a small wavelength, and also X-rays, which are higher energy, lower wavelength than the UV photons that are currently used. Okay, so but jumping back to photoresist, so we're talking about photoresist of traditional UV systems. So what is photoresist, right? The photo is in regards to its photoactive nature, meaning that it contains chemicals that are sensitive to the UV light, and so that UV light produces a chemical change in the photoresist material itself. This change is in response to the pattern, right? So you create the photo change in areas where the light shines, and in areas where the mask is blocking light, you don't create that change, and so you reproduce your pattern in the photoresist. There's two basic types of photoresist, positive and negative. They differ in the type of change that is produced by light exposure. So positive photoresist, the UV light exposure makes the resist dissolve more easily. And in negative photoresist, just the opposite, light exposure makes the resist dissolve more, is more resistant to dissolving. Positive photoresist is used more popularly, but you could build your device either way. And the photoresist itself has several components. First, you have the resin or the base material. This is polymer resin, so you're thinking about, right, you should have a picture of long carbon chains, just like we talked about the first half of the class when we talked about polymer structural materials. So you have this base resin, and then you have generally some photoactive compound. And we'll talk about a specific example in a little bit, but this photoactive compound in general helps to stabilize the resin. And so as you change this photoactive compound, you're either increasing the stability of the resin or decreasing it, which will enable you to selectively remove it later on. And then you have a solvent. So the solvent, as we talked about, gets in between those chains and increases or decreases rather the viscosity, so that you have a system, right, a resin photoactive compound solvent system that has tuned viscosity so that it can flow and create a thin layer on the surface of your wafer, right? The solvents evaporate, leaving behind the resin and the photoactive compound in a thin layer on the top of the wafer. Photoresist is measured by two primary metrics. One is the sensitivity, and this is a measure of how much light is required to elicit the change in the photoresist. Meaning, basically how sensitive it is to light exposure. This is generally very wavelength dependent, and that's desirable, because if you would want your photoresist to be sensitive to, say, the UV photons, but not sensitive to visible light, that way you can have the lights on in your facility and without worrying about curing your photoresist. So sensitivity, also resolution. This is similar. So resolution was a measure of the first half of this photolithography process, where we're trying to have good resolution of exposure of the light. But the resolution, it's a product of both, how finely you can expose a region and how faithfully the photoresist can reproduce or reproduce that pattern. So resolution is also a measure for the photoresist. As far as how they work, there's a lot, probably every different photoresist system has a slightly different mechanism. And here, my intention is just to illustrate a few examples of how they might work to introduce that. But this is by no means the only photoresist systems or mechanisms. But the two simplest ones are looking at the chain length. So the resins are polymers, as I said. And if you have long chains of carbons, right, those chains intertwine with one another. You have higher degree of van der Waals bonding, and that slows the dissolution, right? All of those intertwined carbon chains, it hinders the ability of the solvent or the developer or whatever to get in between those chains and to remove them, right? So that would be giving them good solubility or low solubility beforehand. And then when you shine the UV light on them, that high energy photon can dissociate the bonds in the polymer chain, right? So you're breaking those bonds and taking long chain polymers and creating many short chain polymers. And so these short chain polymers do not have the same degree of chain entanglement. They don't have the same degree of van der Waals bonding. And so the developer can get in between those chains and remove them, and they become more soluble, right? So this is an example of positive photoresist where the light is making it more easier to dissolve the photoresist. Depending on the resin chemistry, you also could use those same UV photons. Instead of breaking up the carbon chain, you might actually use them to facilitate the opening of, say, a double bond and the formation of an additional bond to form a crosslink, right? So if you have short chain polymers and you have all of these UV photons initiating them to bond with their neighboring chain, neighboring polymer chain to form a crosslink, then what you're doing is you're taking a lot of short chain polymers and you're creating one basically huge molecule as they all crosslink with each other. And the more that you do this, the less soluble it becomes, right? Because now you need to remove a big interconnected molecule as opposed to a smaller polymer chain. And so this is an example of negative photoresist where we are adding light and it is increasing the resistance to dissolving in the polymer, right? And so just by breaking up or forming crosslinks, you can elicit that, right? So that's kind of a simple example. A common system, and one that illustrates kind of another way of building a photoresist, is this DQN system. So this is diazo, quinone, and novolac. Novolac is a resin, and diazo quinone is the stabilizer. So this is the photoactive compound. And there's a solvent in there too, but we don't worry so much about that. So you have these novolac resins and you have this DQ photostabilizer. And this is a positive resist. because before light exposure, this photoactive compound helps to stabilize the Novolac resin molecules. But when light is shined on it, right, it dissociates one of its side groups, forms a free radical, rearranges a little bit, and forms a different molecule. And this different molecule is much more soluble in the developer solution. And so it dissolves away and no longer stabilizes the Novolac resin molecules. And without those stabilizing molecules, now those Novolac are more likely to dissolve. So this is another example of a positive photoresist where you're not breaking up the polymer chain. In this example, what we're doing is just changing chemically the stabilizer molecule so that it can't do its job as effectively. You could also, in a negative photoresist sense, think, you could imagine a molecule that had a rearrangement, right, that instead of increasing its solubility, decreased its solubility, right, and then you'd have the same basic mechanism, but producing a negative photoresist where after light exposure it is less likely to be removed, right? And so, for positive versus negative photoresist, you could use either, but you would need a mask that is complementary, right? So if you switch from a positive to a negative photoresist, now every region where you wanted to pattern beforehand, right, needs to become the opaque. So when you switch photoresist, your masks would need to be essentially the negative version of the mask. Okay, so we talked earlier about this modulation transfer function, and I reviewed it a little bit at the beginning of this video, where the light regions are only so bright, and the dark regions are only so dark. And this goes hand in hand with the resins, because the resin is being changed by the light. And that change requires a minimum amount before it will start. There's a threshold that needs to be met before the developer will start to dissolve it, or not dissolve it, depending on whether it's positive or negative. And there's also a degree of light exposure to where it is a threshold above which, right, all of the resin in a particular location will be dissolved. This is referred to as the D0 and the D100 level. And these are important parameters to know, right? So for your resin system, and they're interrelated. So, if my resin system requires a certain modulation transfer function, meaning that the darks need to be a certain dark, it needs to, the dark regions need to be below this D0, and the light regions need to be above this D100, right? So that drives the modulation transfer function that I can accept from my optical system. And so, the photoresist and the source and the mask, and it all feeds together to produce, right, your end product. And here we just have a plot of the fraction of resist remaining. This is from Campbell, both for positive and negative photoresist, right? So here we see this is a positive photoresist because as we increase the exposure, there is less resist remaining, right? So increasing the exposure has increased the solubility, which is a positive photoresist, right? And conversely, we would have a negative photoresist where increasing the light exposure increases its resistance to being removed. Okay. Generally, the contrast that's required, right, the definition of dark, definition of bright, is kind of shown here, right, where we're talking maybe less than 10 millijoules per square centimeter for D0, and then for D100, we might be at, say, 100 millijoules per square centimeter, something like that. And you want this transition to be as sharp as possible, because the steeper the curve, the sharper the edge you can form, which means that you want to maximize the contrast, or the modulation transfer function to the degree that you can. This gives you the sharpest edge. It means that the region over your surface where you transition from dissolving to not dissolving is as narrow as possible. And for reasons of material usage and exposure time and throughput, you don't want to have a thicker layer than is required, because a thicker layer of photoresist requires a longer exposure, more processing time, in order to get to this D100 level where you have either fully removed or fully hardened your photoresist. But at the same time, so you say you don't want to go too thick, you also don't want to go too thin, right? Because the photoresist is there not only, well, it's there primarily as a protective layer for subsequent processing steps, right? So these devices, they don't go into a computer or whatever device they're destined for with photoresist on them, right? The photoresist is removed. Before it's removed, subsequent depositions or etching steps or oxidation is completed to make the pattern permanent. And so if you're going to have the pattern be reproduced on the surface, the photoresist needs to protect the regions that it is covering from that process, right? And so it needs to be thick enough to perform that function. And before we looked at the modulation transfer function as sort of the maximum minus the minimum divided by the sum of the two, and we calculate this CMTF, or the critical modulation transfer function of the photoresist, in a similar way, where we look at sort of the maximum light required minus the minimum light required. This would be for full reaction, and then this would be for zero reaction divided by the sum. You would sort of calculate it in the same way. And so what you want is for the modulation transfer function of your optical system to be at least as high as the critical modulation transfer function of your resin. Okay, so the process for photoresist is always more complicated than you might think, right? And this is probably a simplification in itself, but there's a couple of steps here that are added in to increase the end product, as far as adhesion and cleanliness and so forth. So we have some additional steps in actually doing photolithography. So before you, the first step would be to bake out the silicon wafer. So under normal atmospheric conditions, you're going to have water molecules adsorbed to the surface, and so those water molecules are going to interfere with the adhesion between the photoresist and the wafer, and so you want to get rid of those. The easiest way to do that is just to increase the temperature so that those water molecules will be liberated. Then you can apply an adhesion promoter. So this would be a molecule that is kind of dual functionalized, meaning that part of the molecule bonds well to the silicon surface, and another part of the molecule bonds well to the photoresist. And all of these layers during this process are generally applied via either vapor, where you have a vapor that condenses on the surface in a thin layer, or probably more commonly through spin coating. So spin coaters are basically have a spinning chuck that you put the wafer on, and it spins very rapidly, right, a couple thousand RPM, and then you deposit a small amount of the coating onto the spinning wafer, and the centrifugal force of the spinning, right, will wick that coating across the surface and form a very thin, very uniform layer. That's how the adhesion promoter is applied, and you let the solvent evaporate. And that's also how the resist is applied. So you put it in a vacuum chuck, you spin it up, you deposit a drop of photoresist, and that is immediately spun out to a very thin, very uniform layer. So the amount that you apply doesn't necessarily dictate the layer thickness, right? That's driven by the spin rate. And if you apply too much, right, it's just going to spin off and coat the walls of the inside of your spin coater, which is common, right? That's kind of how you know you have enough. After you apply the resist, you do a soft bake just to remove some of the solvent. A lot of that solvent is going to be removed during the spin coating as you take a small amount and greatly increase the surface area. The solvent will begin to evaporate before you even bake it, but you may want to bake it to remove a little bit more of that solvent. Then you do your exposure, right, where you put it in your lithography system. You have your mask either projection projected onto the surface, or through contact, or I'm blanking a little standoff proximity printing. Then during that exposure, right, you have changed the photoresist chemically. So now in the next step, when you place it in the developer chemical bath, the developer can now either attack the areas that have been softened, if it's a positive photoresist, or the areas that have not been hardened, if it's a negative photoresist. And as the developer is used, it is going to accumulate the resin that it removes, and so its potency is going to decline. And so you need to be aware of that, keep the chemical fresh, control the temperature, because temperature is, as we know, very related to reaction rates, because we want to fully remove the areas that have been exposed above D100, right, in the case of a positive photoresist, but not further than that, right? So you want to have the chemical strength at a predictable level so that your process time is correct. Then after you have removed part of the photoresist, right, you have established your pattern in the surface, and you want to make that permanent so that you can take it and do other processing steps, say etch away the silicon that's exposed, for instance, and so you do a hard bake. Here you increase the temperature, that creates more energy for activation energies for various cross-linking reactions, and will toughen up the photoresist that's remaining and allow it to withstand the subsequent processing steps. All right. So some things to consider about photoresist. So when we are applying the UV photons, right, they're being absorbed. That's what's driving the chemical reaction to either increase or decrease the solubility. So you need to be aware of what the absorption coefficient is, and if it's it needs to be within the right range. If it's too large, then you're going to have trouble penetrating all the way down through the photoresist, and you're going to have long exposure times. If it's too small, then it won't be absorbing and actually driving the reaction, right? You'll have a lot of that UV radiation kind of transmitting through the photoresist, reflecting off the back surface, and then coming back out without being absorbed. And that it's also leads to long processing times. So you need to have the right absorption coefficient, not one that's too large or too small. You want it to also absorb in the UV, not invisible, because this allows you to have visible lights on in your production facility without worrying about changing the nature of your photoresist, and only when you expose it to the UV do you get that change. Also, surface topography of your device is important. When you spin coat, you don't get a uniform coating unless the surface is flat. If you have a step, say for instance like this sketch here, you're going to have thickness of your photoresist that on top of the step and across the corner that is less than what you get on the fields, right? If you've ever painted something with sharp corners, right, you know that the paint layer is thinner at the corner than it is on the flat. Same thing happens here with the spin coating. And so you're going to have different D100 and D0 values for this region. And different removal rates. And so it's desirable to build devices excuse me, that don't have these steps, or at least to minimize the aspect ratio of the surface topography through planarization. This will help in the light portion of photolithography. You don't have reflections at various angles. It also helps with the photoresist consistency. And also, many photoresists, the absorption coefficient is changing while it's being processed, right? So we have unexposed with some absorption coefficient. As it's being exposed, we are chemically changing the photoresist, which is changing its solubility. It can also potentially be changing its optical properties and lead to different absorption. And so this needs to be factored in to the process times, because you can imagine, let's say in this example, we're going from high absorption to low absorption, which means that the back half of the photoresist is going to be exposed to more and more radiation or UV radiation as the process continues, right? So it's going to be kind of accelerating that exposure process, which can have impacts on how much process time is required. And right, all of these resins, all of these photoresist systems are absorptive below, say, 250 nanometers, right? The I line and the G line are like 430 to 450, something like that. And so generally, we'll see this later on when we talk about X-rays, as you go to a higher and higher energy photon, the absorption tends to increase, right? So if you have, let's say you have an insulator with a really high band gap, well, it's going to be transmissive, say glass or fused silica. It's going to be transmissive to any photon below that energy because it's not enough to get across the band gap, and so there's no energy level for, say, an electron to go into after absorbing that photon, so the photon's not absorbed. As I go to higher and higher energy, lower wavelength systems, right, that becomes less and less true. Eventually I reach an energy, say with an X-ray, on the order of a kiloelectron volt, which is well beyond the band gap energy of even even our silicon dioxide or fused silica mask. And so the resonance system, the optics, it's all heavily wavelength dependent. So as we are chasing smaller and smaller wavelengths to get smaller and smaller features, right, we're going to have to keep redesigning basically the whole system, right? New optics, new photoresist, new source, which adds more complexity and it makes it more difficult to get that next level of improvement. Okay, speaking of that next level of improvement, there's a lot more material in Chapter 9 that I'm covering here, right? This is just an introduction to kind of give a flavor of how you would continue to progress to a smaller feature size, and that is shifting from optical UV-based systems to non-optical lithography. These systems, the adoption of these systems is delayed by their high cost and their high complexity, also by the fact that microfabricators are very clever when it comes to maximizing and getting every bit of performance out of optical lithography systems as possible. We talked about some of these tricks in the last video where you'd say, okay, so with the projection lithography system, you can play the same sorts of tricks that you do to maximize microscope resolution using the Raleigh criteria, right? So you have high aspect, high numerical aperture lenses, extreme UV sources giving you a smaller wavelength. We have scanning steppers, which enables you to have a larger feature size on your mask and then just reduce it optically. Immersion lithography, where you're changing the index of refraction of the space in between. So all of these squeeze a little bit more performance out of these optical systems, but at some point, right, you will have exhausted those options, and the transition to a new technique may be required. So two possibilities for that are high energy electrons and X-rays. High energy electrons, a lot of this understanding required for this, it comes from studying the SEM. So those of you who were in 680 last quarter, we studied the SEM, TEM, scanning electron microscope, transmission electron microscope, and we were introduced to how electron beams are generated, how they're manipulated. So rehash a little bit of that here. So you might be a little confused as to why an electron is of any use at all when we had photons before. But just like photons have a wave nature and also a particle nature, electrons have a particle nature but also a wave nature. And so electrons have a wavelength, just like a photon does. That wavelength is defined by its momentum. So this is the expression for the de Broglie wavelength. So the momentum of an electron is the mass of an electron times its velocity. So you can decrease the wavelength of an electron just by accelerating it to a higher velocity. So you do that because you have a charged particle. You can do that relatively easily through a potential difference. That potential difference here is the charge of an electron times the magnitude of the potential difference in volts. And so that energy of that electric field goes into kinetic energy of the electron, and this is non-relativistic. But for relatively low speed electrons, say 25 to 50 keV, something like that, it's a reasonable approximation. So all of that potential energy goes into kinetic energy. So this V goes in here. So as I increase the potential, I increase the velocity, which means I decrease the wavelength. Small wavelengths are good, right? Because I can get high resolution. And the electron gun, we talked about this in SEM, right? You can have kind of two flavors. One, simpler, is just a heated filament. So let's say, hey, I have a tungsten filament in a vacuum, something like that. As I heat it, I'm boiling off these electrons, and they can be gathered up with a potential and accelerated to form an electron beam. Conversely, I could have, so this is called a thermionic emission source. I can also have a field effect emission source where I don't have to heat the tip. I can, I don't have to. Instead, I have a really, really sharp metal tip and a really high electric field. And that makes the field really sharp and a really high extra, like 10 to the 6th volts per meter, something like that, in the vicinity of this tip, which is high enough to essentially pull the electrons out of the material using electric fields rather than thermal energy. So you get a lot higher brightness with the field emission than you do with the thermionic emission, regardless of how you generate the electron beam. Once they're liberated from the material, you can use electric fields to accelerate them. You can also use magnetic fields, so you have electromagnetic lenses here, which is just a coil of wire. So this is kind of a side view. From the top, right, you've got a coil of wire. It creates a magnetic field that goes down the barrel of the electron gun. And as the electrons come out, they swirl around this cavity, and you can either loosen or tighten that swirl by running a current through these electromagnetic lenses, which allow you to focus or defocus the electron beam. You also have deflection plates, so you have a set for X and a set for Y, where you would apply a potential difference here, and that would allow you to raster the beam basically back and forth or through any portion of your wafer to sketch out, right, some sort of a pattern, right, some pattern of electron beam exposure. And of course, this whole system needs to be under vacuum because electrons won't travel on these nice straight paths if there's a lot of atmosphere in their way. And so the electron beam differs a little bit, in regards to optical systems in that you don't expose the whole surface at the same time, right? You have to scan over the surface, or you can direct, right? Where either scan over the whole thing, and where the photoresist is, the electrons won't reach the surface, similar to the optical lithography. Or you can have direct write systems where you only raster over the ports that you want to write, which I guess could not require photoresist at all. Electrons, it's a little bit different than, because they're particles. Before we were talking about photons being absorbed, so you have this absorption coefficient, and the intensity is decreasing exponentially via Beer's law, according to that absorption coefficient throughout. With electrons, you don't have like absorption like you do with photons. You kind of think of it more as electron scattering. And you don't have the maximum number of electrons, say, at the surface with like a gradually decreasing or exponentially decreasing curve. Here you have kind of a probabilistic scenario where you've got this scattering, and depending on the energy of the electrons coming in, right, they will run out of energy at a certain depth. And so you have a Gaussian distribution in depth, and you also end up with a Gaussian distribution in the planar direction as well, right? As these electrons go into the surface, they take a random walk. So every time they have a collision, they change direction. And over many collisions, right, they can end up far away from the impact site, say off to the side or into the material. At any rate, you have this probabilistic Gaussian distribution both in depth and in horizontal extent in the surface of the wafer. Depending on how thick your wafer may be, right, a lot of this, the bulk of these electron depositions might be into the substrate below it, which is not as big of a concern as the Gaussian profile in this direction, right? Because if you are sending them into a very small region at the surface, right, you might think that, oh, I'm just affecting the photoresist here. But because of this random walk, right, you may have a region below the surface that is much larger than the impact region, which will impact, the resulting quality of the pattern that you are producing. So electrons, you can get a really small wavelength, which is good. The bad part is that it is slow, right? I can only expose one at a time, and I have to raster my beam around. So that's okay for applications where I'm only making one anyways, right? So if I want to make a mask, for example, that I'll then use in an optical system, right? E-beam's okay, because I only need to make that one mask, and I can use it thousands of times. Or if I'm making a prototype, just as a proof of concept. But for production, E-beam systems are slow because they're not parallelized, or it might take an hour to make one wafer as opposed to a few seconds exposure with a UV system. So it's too slow to be economic for devices. You can speed that somewhat a little bit by having stencil masks. So if you're creating the same type of pattern over and over again, right, I can expose through a stencil and not have to direct write the beam. Or you can vector scan and only, like I said, expose the areas where you want to write as opposed to everything and relying on the photoresist to block the regions, or the mask rather, to block the regions where you don't want to expose the photoresist. Okay, and I already talked about this proximity effect. So, okay, I got about 46 minutes. I'll finish up here by talking about the second non-optical lithography technique. That would be X-rays. And an X-ray is just essentially a higher energy photon than a UV. So if you keep going lower and lower in wavelength, higher in energy, eventually it's not classified as a UV photon anymore, right? You've entered the regime of soft X-rays, which have wavelengths that are even shorter than the deep UV, which I guess is the natural extension of chasing after lower and lower wavelengths, smaller and smaller wavelengths. To generate X-rays, you need a different source, right? We're not looking at a plasma or a gas discharge. Here we need a different source. So some of them that could be used are electron impacts. So this would be how the X-ray gun was operated for X-ray diffraction. We talked about in Material 680 last quarter, where you take a high energy electron beam and you impact it on a metal target, and you can generate X-rays because those electrons knock out inner shell valence or inner shell electrons in this target atom, the atoms of the target metal, and then higher lying electrons fall down into that vacancy and emit the energy difference as an X-ray, as a photon. The energy difference is large, and so you get an X-ray photon. That is one of the interactions that can happen when a high energy electron impacts into that metal target. There's a lot of other ones. Regardless, that electron needs to slow down, and so it gives up a lot of that energy as heat. So this electron impact heats up the material quite a bit, pretty inefficient. You can also generate X-rays from a plasma. So if you use a pulsed laser or electron discharge, you can create a metal vapor above a target, superheat that metal vapor, and that will create a plasma, which will emit X-rays. You can also use a synchrotron storage ring. So you've got a ring with electrons that are confined and accelerated with magnets. So this is expensive, especially if you want to have a small ring or really powerful magnets, because you have to have essentially really big electromagnets that are cooled, use a lot of energy, or superconducting magnets, which require supercooling with liquid helium, which is expensive. At any rate, as you move from electron impact to plasma to storage rings, you get more intensity, but you also get more expensive. Using X-rays is a great example of having to redesign basically the entire system to accommodate that lower wavelength. The optics become a problem. The reason that glass is transparent to visible and UV photons is that the band gap of silica is like 9 eV. So that's too high for optical and UV photons to take an electron across the band gap. So that photon is transmitted. The problem becomes when you get a high enough photon that it can actually take an electron all the way across the band gap. So instead of being transmissive, it's absorbed. So you can't build optics out of traditional materials for X-ray systems. And so you need a new way of reflecting, focusing these beams for use. And you can make an X-ray mirror out of take a metal mirror surface at a high enough angle will be reflective of the X-ray. Right? You can have basically glass capillary tubes that kind of act like X-ray waveguides and will redirect the X-rays. Or this is probably a more popular approach. You have a multi-layer mirror where you have alternating materials of high and low index, and the thicknesses are chosen to create constructive interference in a certain direction for a certain wavelength. It's kind of like a Bragg reflector. So you need a fancy mirror for X-rays, and also creating a mask is more difficult. Because the X-rays are absorbed, it's difficult to find a mask that has transmissive regions. And so you're stuck with trying to use a mask that is very thin, which is more difficult to work with. It needs to be thin enough so the X-rays, some of them can get through. And similar to electron-based systems, with these X-ray systems, throughput is an issue. It's very slow. You do one at a time. And in addition to needing new optics and new masks, right, X-rays also require new photoresists. So when you have these really high energy photons, yes, the wavelength's really low, but there's lots of energy there, and so you get more reactions within the photoresist than just your target reaction, where you're say destabilizing a molecule that makes the resin more soluble, or doing chain scission, or facilitating the formation of crosslinks, right? Now you've got all of these higher energy. You're creating photoelectrons. You are, you have Compton scattering. You've got, all of these other things that can happen, and that affects the reactivity of the photoresist in a negative way, usually. X-rays, you can also be creating radiation damage in the semiconductor itself. So this is probably similar to what we talked about with ion implantation, where you're depositing a lot of energy, and that is disrupting the crystal structure of the material. So you might end up having to do like a post-lithography anneal the same way you have to do a post-implantation anneal. So that just about does it for time, right? This lecture, to review, right, we focused on the photoresist and introduced a couple of non-optical approaches, right? The name of the game being getting to lower and lower wavelengths so that you can have good resolution at smaller and smaller feature sizes. All right, thanks.